All right. To break of a tradition of starting late, looks like we're filling up, so get started. So if you're in the right place, then this title will look like what's on your little slide. Zipkin is an interesting word. If you Google it, you'll probably see things about distributed tracing, but it's more interesting if you translate the word Zipkin. We'll talk about it later, but to save you some Googling, it's a harpoon. And because it originally started as a Twitter project, you could imagine what it's trying to kill. So, sneak peeks aside, I'm Adrian. I work at Pivotal on Spring Cloud stuff. So definitely was interested in hearing some of the previous presentations. A lot of people talking about Spring Boot and things. I do work on some of those things. I'm focused on distributed tracing, though, and particularly an open source project called Zipkin, which we'll get into a bit later. For the I think for most people, this idea of distributed tracing is a little bit ambiguous. So I'll go ahead and try to tiptoe into it. At the end of the day, we've heard a lot of presentations and people talking about microservices and the sort of transition into granularity. So we start off with monoliths and we're kind of breaking them until we get more and more pieces. And when these connect across the network, we end up with a graph, whereas before we may have had a big server. The nice thing is that it's easier to reason with each of the parts, but one of the troubles that come with that is that the flow between these parts can become delayed or can have errors, and depending on how the architecture is modeled, they can be easier or more difficult to understand. So like one of the things that I think microservices is sort of pushing us towards is a time where we really need to understand our architecture a lot better and a lot more currently than we had in the past. So it's not usually something we can draw on paper anymore. And in the case of functions, and I think Latency's service graph of 4,000 services, it can be quite compelling to look at tools to help us with this task. One of the things I like to do is break down problems into simple things because I think our world is full of cognitive overhead. And for tracing, I'll try to walk through it with just a normal post request. So, often enough, when something's slow in the browser, there's a post involved. So I use that. And when we think about latency, it's not as simple as like, was the request slow? It's at least what side of it was slow. Was it us doing the call? Was it the server receiving the call? And if I'm in a troubleshooting task, I may have a view that some things are perfectly fine, but the user's view might be perfectly not fine. And so even just microservices aside, just a simple post request can be an interesting problem to dissect. So when we look at like latency in general, we've got this. We also have some interesting decomposition issues, like which operations that are behind these like post requests are on the critical path, which are asynchronous, what are intentional operations or what are accidents. So there's a lot of tools now that can help us with fallback values and automatic retries, and I would call those like accidental tasks. Like we don't really want to retry 5 times. It's that something had failed, and then you're trying to resolve transparently. So when we look at the breakdown for this, in this case, like a a waterfall view of sorts, we could see that maybe this post on the client side had redundant operations trying to send this thing across the wire. And maybe that's a problem because it should have only gone once. And then we could see on the server side, which I've done in green for the people who are colorblind, that maybe someone has previously done some optimizations to make sure that storage is asynchronous, and so that it doesn't block the client on the way back. So there's a lot of interesting stuff about latency, like what's intentional, what's unintentional, and it's easier when we can see these things visually. But this is kind of a rosy view because most of the time we have more things than we want. Maybe there's some distractions. If anyone here has done any Java development, you probably have done a stack trace and seen all sorts of weird things, event loop -2 things and poorly named threads and ancillary processes going on. So it can be difficult to kind of weed through that to see the difference between operations going on, what's adding context, and what's just distractions. So I think like when we look at just latency in general, this probably isn't too surprising for folks. We're used to looking at overall time and splitting it between what a client and a server would be aware of. But I think it's interesting to look at this piece because when we get to a distributed network, you have much more of these. So when we look at a post request, maybe it fans out across 200 services, and what happens if the third request deep doesn't operate? If we don't look at things carefully from even just one request, how could we do that with a more complicated network? Because at the end of the day, it's not simple anymore. Single server scenarios aren't very realistic, and they certainly don't fully explain latency. One of the things that I think a lot of our front-end devs will have like a Chrome debug and some other tools to help break down what their views are. But they usually have some sort of limitation. They get to the point where afterwards there's a bubble. One thing I've been always interested with a lot of tools is that as we get more advanced with what we can deploy, we need to be equally or better at there are tools to manage that or help us understand it. So I'm pretty impressed with what we can deploy these days and how easy it is to deploy. And you can create graphs of networks, which, and you can pretty much run a Spark job even if you have no idea how that works. And the sort of the responsibility we have to this is the troubleshooting side. Can we make triage, troubleshooting, resolution of issues as accessible as the deployment? And I don't think we've done quite well enough here, frankly. I think that we focus a lot on the first starts, and tools, Docker, and all these other things are quite easy to get started. And I'm not saying that there aren't great tools out there, but I don't think it's always coupled with the operations and how we can save ourselves from having to be experts in everything. So I think that's one of the challenges that tools like distributed tracing can bring to bear to help, as we start getting more complex networks. I mean, like other things, I think distributed tracing commoditizes, or it aims to commoditize knowledge. You're gaining knowledge about what your system's actively doing, and unlike normal metrics, you get a sort of happens before relationship, like not just this endpoint has P99 200 milliseconds or something like this. It's that all of the requests that we know about that hit this, the following were caused by this process, and knowing that causal relationship is commoditizing a different type of data than like metrics or just logs. And when we know more about the causal graph, about why what hit certain servers or which functions, we can start to understand our networks better. And then we can use this data to help understand why something takes longer than something else. In distributed tracing, jargon is there. I think probably the word that most people don't use often is span, so I wanted to take a little bit of time to talk about that. So a trace is basically if you start with a REST request and it fans out into 15 database queries, the trace is that entire operation. Doesn't matter how many services or lack of services it hits. When it completes, everything that branched out from there is in the same trace. A span is like one thing inside of it. So if I were making a request to post things and it ended up hitting MySQL, then there'd be one span for the post and maybe one span for MySQL. Unless the connection failed, then I'd have another one for the retry. So this is the things that we use to sort of construct a trace. And it's important to remember like what the trace is. Like what we're trying to do is like, we're trying to draw something that looks pretty much like what it actually does. So it's a fairly good analogy that if a trace is good, it's unsurprising when you look at it from what actually happened. So this span, if I were looking at an HTTP request, then I would have some pretty typical information like maybe the HTTP method and the endpoint that was hit, the specific node in whatever cluster that it was on, and then notable events like the server received the request or sent a response. And then because we need to understand context, we would usually add tags to that. So minimally, we might have a response code to see if it was like a 500, but we may also have things like like a customer ID or a debug ID that we use across our other application components. So that way we can go back and look up things. And so if we're trying to query for a specific problem case, we can aggregate based on tags. And tracing, I put in the same bucket as other observability tools, like your normal metrics. And the biggest difference here is that unlike metrics, which are usually sending data that increments based on like a context, like a HTTP path or something, this is collecting the causal data. It's having to know the service or the component that was responsible for this request, and therefore it has a tree structure. So like a normal metric, you can just think of it as a label and a number. Minimally, that's what you need for normal metrics. But in tracing, you actually need some sort of a structure, like usually a tree, to show the relationship between this thing that was hit, what called it, and what it called. Another difference between tracing and other observability tools is retention. So like it's not like a logging system which you'd retain for long periods of time. Usually the retention is a couple of days. I think at Twitter it was 3 days on index and 7 days on data. Some people have just 48 hours. So it's a sort of like triage troubleshooting tool. And it's usually not retained for long periods of time. And like most things, there's some query and visualization tools. One of the funny things that you get when you start having a data structure that tells you what caused what is that you realize that it's not just latency that this is interesting. For example, you may not know what your architecture actually does until you see a trace of what actually happened. And it sounds like you should know, but sometimes it can be quite surprising because configuration might have buried 3 levels deep what memcache should be doing, and maybe memcache was never actually turned on, and you thought it was. So you can get a better understanding of your architecture and what it's actually doing versus what you think it's doing. There's people who use tracing for things like knowing whether a deprecated service is still in use. We do have like alerts on services, and we're sending it heartbeat traffic, and you might look in metrics and you say, okay, well, version 1 of this API, that was supposed to be turned off a month ago. Why is there still requests to it? And of course, you can go back in the logs and you can grep around and try to figure this out. But you can also use tracing to see like what actual component was calling that, for example. So it can take some of the sleuthing out of the process. My favorite thing about tracing, which I use in developing tracing, is just reducing time spent on triage. We're very inventive as engineers. We can figure out all sorts of hypothetical scenarios to explain a problem. And sometimes we can get really dug into those theories and argue for a long period of time about what caused this. This was the database, or this was, no, definitely the network. And when you end up with a realistic view of service calls and what called them, then you can instantly dismiss some theories, and you can get to work faster. And so I kind of feel like, even though I put this as the last, I feel like that's the number one, which is just reducing the undifferentiated discussion. And there's all the other things I didn't put down here. For example, I left Twitter about a year and a half or 2 ago for Pivotal, but right before I left, I knew that we were using Zipkin to debug the latency of Git. So if you have a mono repo and you have like 1,000 developers who are like doing Git pull, and it will be very, very long and it will really clog up everyone. So they were able to understand why the source control was slow and delayed based on using tracing. And I've noticed some of the people in the community are also using this for like the Gradle builds. So they'll figure out like, why is the Gradle build so slow? Now, it's like everything else. You can look at logs and you can parse them and you can do your own little math. But it's nice when things are structured and they already have latency applied for you. So I think that tracing is like latency is one feature of distributed tracing, and for a lot of people, probably understanding is the bigger one. So Zipkin is a distributed tracing system, and I kind of tried to tease about the word Zipkin. Zipkin is Harpoon. Zipkin was created when there was a lot of failures on Twitter in the early 2010s, and so there was the fail whales, and so you want to kill the fail whale, and found that the latency was one of the biggest causes of failures. And so this was a system to try to help inventory latency data and make it queryable. This is a real trace. I think actually this one is from Uber, I think. But you would be able to get like a timeline view of the top, which is the critical path, and then what that breaks down into. And on the left, like there would be a bar with like the service names and how they contributed to that. So in this case, like it would say there's 20 some different operations that fed into. At Twitter, I think some of the requests could go into like 200 or 300 services sometimes. So visualizing that sort of stuff can be tricky, but it's certainly nice to have a tool that you can use that regardless of like how many services you go through, you can use the same. So I can use this like in a MySQL database with it's only going for 3, or something that's quite complex. And so it's nice to have a single pane of view for that, I think. Zipkin is living in GitHub. It was a product that was internally managed by Twitter until I was there, and in 2015 we moved the the Zipkin project into its own like GitHub org. And it was an interesting thing, but basically over time, the community ends up with more experience in the tool than the original authors. And so in a way, if you wanted the best thing for Zipkin, it would be moved to where the people are. And so it was a very nice thing that Twitter did. And so the Open Zipkin org has a bunch of things in it. I'll review some of it. Like for example, I think the thing most people might be looking at, whether you're a developer or manager, is like what does this look like in my network? And this is just a grab from the architecture page. And at the end of the day, when you're collecting this trace data, something is like harvesting the information from your apps and pushing it into Zipkin somehow. The architecture is very similar to like a normal metrics reporting architecture. So something's collecting and pushing metrics onto some transport, and then it's being processed. In this diagram, the things that are like, I would say like the core Zipkin stuff are in this dashed box. And then the kind of purplish lavender things are like client apps. When we say client apps, it actually, these are services. So this would be like your inventory service or your profile service or whatever. They're the things that are collecting data, and they're sending them somehow to Zipkin. When I first worked on Zipkin, the only transport option we had was Scribe, which was like a Facebook log aggregation thing. And so the first thing we had to change was that, because nobody used Scribe. And so it's much more often the case people are using either HTTP or Kafka or something else to like schlep data across their network. So we have a lot of plugins for that. And as software, Zipkin is actually quite simple, I think. It has a feature to accept data, which is as simple as a post endpoint. It has a UI, which is JavaScript, an API. They're not surprising parts. And so we do our best to make sure it can be deployed in most environments. I've listed some of the sort of keywords of projects where we have components. So for example, you can use Amazon SQS if you want to send data across that way, or Azure's Event Hub. Everything's, of course, packaged in Docker containers. Google have a trace product that you can actually integrate directly with, and of course, all of the usual suspects of container managers too. So we try to make sure that it's something that is not difficult to run. And I think the biggest thing about tracing I found is that you want to make sure people are focused on tracing and not like how hard it is to start your thing. And so we have a starter architecture. For those who are familiar with Docker, you'll see this is actually a Docker compose file. And you can start with just using MySQL, which is how a lot of people do. And in fact, you could use in-memory if you wanted to. But so we try to make it easy for people to get started with, and that way you have a chance to figure out what it is before you invest in figuring out Kafka or whatever. And it can be even simpler than that. Zipkin is a Spring Boot app, and so you can just download the jar and java-jar, and then you have a Zipkin server. And so I'll use that in a demo in a few minutes too, but it's quite easy. I showed earlier the architecture, like what it looks like in abstract, applied to like a flow diagram. This is what happens. So you usually would have like some user code that's asking you to do something. Like I have a REST library that's going to like hit this endpoint and do like a get. And usually trace instrumentation, regardless of whether it's via an agent or via it's a configured library, there's typically an interceptor pattern of some sort that's in play. And what's like relevant for tracing is like adding tags, which might be lookup in nature, because this is important to go across the network, you need to be able to propagate that trace ID. So it's usually using like HTTP headers. So like in this case, the most commonly used HTTP headers in Zipkin are these like x-b3 prefixed headers. And B3 stands for Big Brother Bird, which was the name of Zipkin before it was Zipkin. And then, of course, getting down to like the recording timestamp and duration. Because, like many other Dapper-based systems, which is the paper that Zipkin was based on, they try to be like always-on type of thing. It doesn't actually send data to Zipkin in the middle of your like REST call, because that would slow down your REST call and potentially make it fail. So all of the instrumentation projects, as far as I'm aware, do like send things to Zipkin asynchronously. So after the request is finished, sometime later, the data gets schlepped. And sometimes people are thinking about like metrics. So what's my backlog? Like how long do I have to wait for data to show up? It's usually seconds, but it depends on how you how your pipeline is set up. So it's something that you can sort of like hit and watch it in near time. So demo time. We're going to use a very sophisticated architecture of a browser calling an app that calls another app. And this hopefully should drive in a little bit of how tracing works and something that you can do. This will use two different libraries. Of course, I could use many of them. It can use, like, there's Zipkin instrumentation for Python, Ruby, everything. But I'll use JavaScript and Java. And so on JavaScript, we use Zipkin.js, which was written by Eirik, who used to work at Finn, who did a presentation. There was a presentation on Finn yesterday. Very nice library. And we have an example project, and this one the example project just has some embedded JavaScript. So when the browser does like a API fetch, the trace data will be recorded. And on the other side, there's Spring Cloud Sleuth, which is the Spring Boot plugin for tracing, and this will like capture that and then send it across a couple apps. And in OpenZipkin's GitHub repo, there's a whole bunch of things like ending in -example. One of the things we try to do is make them interchangeable. So the demo architecture, regardless of whether it is Go or Python or Ruby or whatever, it's always the same apps. And so you can do a Node.js, like in this diagram here about front end, back end, but one in Node and one in Java, and then swap it with Python, and just to play with, and because we understand it's increasingly the case that people are polyglot. So let's see if this transition works. So I have here, I'm going to do mirror screen actually. Give me a second. Okay. So I've already done like git clone. And in this case, there's actually quite I think the network probably works. So I'll show you what the demo looks like. So for example, we talk about like what things should look like and how to run it and all that stuff. So let's start with the browser. So in Zipkin.js, it's one of those fancy, I forget the term, I always forget it, but there's a word for a JavaScript library that works both in Node and also in the browser. Someone might remember. But anyway, it's not always the case. Like JavaScript is not JavaScript. Was it? Isometric. Yeah, okay. So fancy for like actually works. And so it's if we look at this index HTML, I'm just calling this thing bundle.js, which if I grep bundle for README, it's browser.js is the file I have. Let's see if you can see this. So I create like a Zipkin wrapper, and I call a service named browser, and then all I do is I basically use this super fancy functional composition to just print out what the API call sent me. And so the first thing is the browser is going to try to call port 8081. And so I'm going to make port 8081 exist quickly. So in this case, I'm going to do copy paste. And I'll show you the code in a sec. And then that one's going to call another one, so I might as well do that too. And then I said Zipkin is a jar file, so I'll just java -jar Zipkin and start that up. So first I'm going to open the index.html file, and you can see my UX skills at their best. This application is very interesting. As I know I probably should explain this. So what happens is it prints the date and returns it as text. And I'll open the browser. If I go to 9411, which is Zipkin's favorite port, and I'll see that I can search for things that hit the back end, the browser, or the front end, and find trace. And I found that, okay, well, I have one trace here, and it took 240 milliseconds. And now let me do this. And then I'll find again. And so now I have one that's 36 milliseconds. So first off, as engineers, we could guess why one's 236 and 35, and we probably have a bunch of interesting answers for that, right? So who wants to guess before we look and see what really happened? Any guess why one is, wow, a lot longer? Okay, startup time. And then we'll do it again. And let's see, we've got now, we've got another one, and that's even shorter. So there's definitely some interesting stuff. But let's look and see what's happening here. So if we say it's startup time, then we should be able to see some evidence of that. So the client sends at roughly the beginning 140 microseconds since when we thought it began, and then 60 milliseconds later, the server received the request. And it sent its response another 120 milliseconds after that. And then, about 60 milliseconds later, the client receives it. So that's interesting. Let's see what the other one did. Much quicker, at least on the way there, right? So we're talking about, 1 millisecond plus some change. And the way back was quite a lot shorter, 4 milliseconds. And then the last one is probably even quicker, right? Yeah, about the same. So we know at least one thing happened, which is that the network got a lot quicker somehow, from 40 milliseconds to 1. So one explanation for that could be like HTTP keep alives or something. Like the first network connection, even if it's local with no SSL, is probably going to take longer. But it also could be just that the time for the application to respond was slower. We don't actually know for sure whether it was the slow network or the application winding up. But I would say that startup time is a very reasonable explanation. If we look at the back end, it's spending 7 milliseconds of the total request, in that one, and then in the long one, it's 101. So I think that there's some evidence that the warm-up stuff is at play a bit. So this is some interesting things. If I were looking at my network and my network only consisted of what I just shown, then this is what my arc view would look like. If you have a real network, it would be just this mess of lines. And then I could see like, okay, well, if I was looking at the link between the front end and the back end, it looks like that was called 3 times. It might be useful for me. Because everything's uniform here, I'm not fanning out, or I would expect the same thing between the browser and the front end. So this is just a walkthrough of a few things in Zipkin itself. You can get a little bit better at it and start reading, like from the critical path point of view. Since my primary view here is the browser, 100% of the critical path was experienced by the browser. And if I was looking at the back end, you could see that a smaller allocation of that time. It's unsurprising that the browser is going to see the most. But if you have like a tiered network, then it's kind of some helpful triage stuff. Anyway, that's the demo time. So like I think from wrap up, like tracing is one of those things where when you play with it, you sort of realize these emergent type of things that are more useful than they seem. Like understanding, like, oh, my application is making too many requests, and just seeing that in the first place is enough to get some quick wins. If you're already using some commercial vendors, then you probably have some sort of a tracing capability. One of the things that's nice about Zipkin is it's open source, so you can just start it and work with it without without going across the network. You can do it right on your laptop, as I have, like all sorts of technology spaces, it can get really complex. So like if you look at the way that if you're like writing tracing system for Google itself is going to be much more complicated than my laptop. So we try to like phase in things like advanced sampling and advanced pipelines and streaming. These are all types of technology spaces that are interesting with tracing, but you don't have to do that in the first thing. If you are interested in this, we in the Zipkin community, we use this tool called Gitter, which is sort of like Slack or something else for GitHub. And we kind of watch this a lot. So if you have questions that you want to raise later, or you're just trying it out and it doesn't work, you're not alone. You can just bump us there. I think I probably have a couple minutes for questions at least. So if anyone has any, please do ask me anything.
Hi, thanks for the talk. So you mentioned that Zipkin can use different backends like MySQL or in-memory and such. Wondering like which one is the most adopted one or recommended?
Yeah, so good question. So which storage option is best? So we have a couple popular ones. So MySQL is popular to a certain degree. You can actually get like test projects and even some smaller scale production, you can use the MySQL one. It's actually designed so that you could do like SQL relational queries. So it's not designed like you would a high performance table scheme. It's made so that you can understand the data. So, but like say you've outgrown that, then the two most popular options are Elasticsearch or Cassandra. And that really just goes down to what your team's more comfortable with. A lot of times we find folks already have like some sort of a Logstash or some other thing that they have Elasticsearch, And in that case, they probably want to continue using that. We have a few neat things for Kibana, like so we do an extra key in the JSON, so you can cross them in Cassandra not so much, because Cassandra is often used for like log type of stuff. So, but the most mature one is Cassandra, but probably the most active one is Elasticsearch.
More questions? Hi, I have a question on the corresponding ID that define the traces. Is it right that the first instrumented code produces the ID, and every component has to be instrumented? Is that right?
Right. Well, so it's true that the trace ID is the thing that's consistent from one hop to the next. So if that isn't sent, then it will appear that it's multiple traces. So it's important that that propagates through. And then there's a secondary thing, which is identifying which step you are. That's, it's nice to have that work, but less important as the trace ID. So if you think of it, basically you can either be instrumented, which means that you're actually doing things like this flow might show, or you treat it transparently, just like any other like cookie that you don't pay attention to, but it still exists. So like a transparent proxy might just push the same headers that it saw across without interfering with them. And so, yeah, it's true that the trace ID, in fact, whether the trace is being recorded, which we call sampling, that decision tends to be consistent across the whole operation.
One question about instrumentation: is it done on the compile time or on runtime?
So the question about instrumentation, compile, and runtime, well, it could be actually quite kind of both. If you're using agents, then it could be like woven in and then fixed. But I would say that most of the Zipkin instrumentation are library configuration. And so there would be an interceptor that is like a fixed library. So it's not doing like reflection or anything else like that. But it is a configuration decision as to whether to enable it or not. And so I didn't show it here, but for example, in Spring Boot, actually this might be hard for me to, but in Spring Boot, you can choose to do things like parameterized, like with beans. You can also just use properties and choose like things like sampling percentage, whether to turn something on or off. So usually there's either a configuration or a library-based approach. But yeah, I think it's almost never reflective because if your trace instrumentation has a lot of reflection, then in itself could become latent. Yeah.
Okay, more questions?
Have you had any kind of way of integrating kind of legacy applications like MySQL or like Postgres? Have you seen anybody do the instrumentation inside the database, or? So inside the database, less. So for example, I think the only one that I'm aware of, the only data store I'm aware of that has like Zipkin instrumentation inside is Cassandra at the moment. That's because we have a Cassandra committer in the project. But the other side of it is like, how do you deal with things that aren't instrumented? And so you kind of like think of it as a boundary case. So you can still capture your client activity
even if you can't drill down into that. One of the things I found is very nice is that some of the cloud service providers are starting to look into tracing, like you may have seen, like Amazon X-Ray and Google Stackdriver. And there will be a time in the near future, and for some as near as now, where you will get a breakdown of like what time was spent in DynamoDB versus like Bigtable. And I think that sort of behavior will increase the demand to make more services like instrumented in a way that you would be able to see that in your graph. I think like it's only natural, because if we're thinking about deploying and like collaborating with other services, you know, it'd be just nice to see details on those as well to help explain why something was slow.
Okay, any more questions?
Zipkin let us to have a look at trace of request, but I don't think that anyone comes to work at the morning and starts to look into this Zipkin. So my question would be, is there any integration with monitoring tools which lets me know, okay, now my server is too slow, I have to go to the Zipkin and find out why?
So in summary, it's like, sort of like what is the transition between something like Zipkin and my normal metrics and alerting system? Yeah. So I know at Twitter we didn't treat Zipkin the same as metrics, mainly because Zipkin is a bit lossy. So it's sampled like depending on you might get 1 out of 100. So it's not necessarily something you want to break glass over. So it's more like a triage tool after that. So if you are capturing data where I think if this is still up, you could see that maybe there's a HTTP path that's correlated with my something that I'm alerting on, then you would be able to go into Zipkin and then search based on the same path, like HTTP path equals whatever. So if you have a well-defined common dimensions that like common tags that are used in your metrics, then you would be able to transition across. Similarly to how you could transition from metrics to logging if you have some common dimensions to do that. So I would say that that's sort of the way. There are commercial APMs who basically everything you can see, you can click and add an alert on. So I'm not saying that it's not possible to create a distributed tracing system by which you could do 100% sampling and create alerts, just that I don't think Zipkin is currently, the open source project is made to do that.
Thank you.
Sure.
Okay, any more? So, thanks a lot for the presentation.
Okay, thanks. Thanks for the questions.